In this video, we're going to start talking about units of concentration. When I say concentration, we're actually talking about how much solute, so an actual number, that's dissolved in a given amount of solvent or solution. And we've already looked at a couple. We've looked at molarity, right? Molarity was moles of solute per liter of solution. And then we looked at mole fraction, which is also a way to express concentration. Right? It's the amount, right? The number of moles of my component per total number of moles. So how much of one is in the total. I do have a handout, I'm going to pull it up here, that I have posted on Canvas for you that has the units of concentration on it that we're going to be covering. So percent concentrations, and we're going to look at these in three different ways. We're going to look at it in terms of mass, in terms of volume, and then mass volume. And then parts per million, let me get my highlighter here, parts per million and parts per billion. And we're also going to look at those in terms of mass volume and mass volume percent. And then mole fraction, which we've already talked about, molarity, which we've already talked about, and then molality, which is going to be a new one for us. Be really careful, and I will say this a couple times, not to get molarity and molality confused. If you're just looking at the two words, make this a little bit bigger so you can see, right? There's only a one letter difference between them, right? This one has an R here, this one has an L, and then from an abbreviation standpoint, one's a capital M and one's a lowercase m. So just be really careful to keep these straight. Both of them are moles of solute on the top. Molarity we know is the volume of solution on the bottom. Molality is completely different. Molality is going to be mass on the bottom instead of volume, and it's actually going to be solvent instead of solution. It's the only unit of concentration that we're going to cover that actually has solvent on the bottom. So do be careful not to get those two confused. So a couple that we know already, and then a few new ones. I'm going to cover the percents and the parts per million and the parts per billion kind of together. So I'm going to essentially replicate this handout. So if you don't want to write it down, it is posted on Canvas. I would recommend taking notes still, however. So units of concentration, I'm going to do percent, which means literally if you were to translate it, per 100, right? Centi is 100th, right? A century is 100 years. If you think cent, 100 is what this is. So percent is per 100, which is going to help us if we remember this. So per 100, parts per million, which is per million. You can think of percent as parts per 100, right? So parts per 100%, parts per million, which we abbreviate ppm, and then parts per billion, which is literally parts per billion. ppb, not m. So percent is parts per 100, right? Parts per million is parts per million, parts per billion is parts per billion. The reason I'm making a big deal out of this is that we're going to set them all at the same. It's just that if it's percent, I'm going to multiply it by 100 when I'm done with the fraction. If it's parts per million, I'm going to multiply it by a million or 10 to the 6. If it's parts per billion, I'm actually going to multiply it by a billion or 10 to the 9th. So let's actually write that down. So this is going to be 10 to the 6 because that's a million. 10 to the 9th is a billion. We could do 10 to the 2nd, right? If we wanted to be consistent. So mass, I'm just going to do by mass. So it could be mass percent. It could be parts per billion by mass. It could be parts per million by mass. All of them I'm going to set up exactly the same. It's just that I'm going to multiply them by a different number when I'm done. So by mass first, I'm going to do mass of solute over mass of solution. Be really careful, it is solution on the bottom, not solvent, right? So if I was to take 50 grams of sodium chloride and dissolve it in 1,000 grams of water, it's 1050 that goes on the bottom, right? It's the solution. Remember, the solution is the total. It's the solute plus the solvent. We could write that up here to remind ourselves that. Solution equals solute plus solvent. The biggest mistake that I see people make is forgetting to add those together for the bottom. It's solution on the bottom, not solvent. And then if I want to calculate the percent, I'm going to multiply it by 100. So if I wanted mass percent, I'm going to take mass of solute over the mass of solution, and I'm going to multiply it by 100 because percent is per 100. If I want to calculate parts per billion, I'm going to take mass of solute over mass of solution, and I'm going to multiply it by 10 to the 6. If I wanted to calculate parts per billion, I'm going to take mass of solute over mass of solution, and I'm going to multiply it by 10 to the 9th. That's the only difference between those. So if I'm calculating percent by mass, part per million by mass, part per billion by mass, mass of solute over mass of solution, and then multiply it by its corresponding number, right? Do I want percent? Multiply it by 100. Do I want it out of a million? Multiply it by a million. Do I want it out of a billion? Multiply it by a billion. From a unit perspective, it doesn't matter what they are as long as the units on the top are the same as the units on the bottom, so they cancel. So units for solute and solution must be the same. Again, it doesn't matter what they are. They can be grams, they can be kilograms, they can be ounces, they can be tons. It doesn't matter as long as it's a unit of mass and they're the same, because they are going to cancel. I'm not going to have any units on my answer, just either a percent sign is how I'm going to express percent, and we'll do examples. For part per billion, I'm just going to actually put a ppm at the end of it, and for parts per billion, ppb. We'll do examples after I go through all the types. We can do it by volume. So all I'm going to do is change the words mass above to volume, and it's going to be exactly the same. So volume of solute over the volume of solution. Again, remember the solution is the total, so solute plus solvent, right? If I was to take 50 milliliters of ethanol and combine it with 100 milliliters of water, 50 milliliters goes on the top and 150 milliliters goes on the bottom, right? The total. And then if I want percent, we're going to multiply it by 100. If I want parts per billion, I'm going to multiply it by a billion. Or if I want parts per million, I'm going to multiply it by a million. So the same thing. The units for the solute and the solution must be the same. It doesn't matter what they are, they just have to be the same. So if one's in cups, the other can also be in cups. If one's in liters, the other's in liters. It doesn't matter. They just have to be the same. And they're going to cancel. So I'm not going to have any units on my answer. So by mass, by volume, and then my last one, and this one is going to be a little bit different. This is mass volume. Sometimes just as abbreviations, just so you see it, sometimes they'll actually put like a little m/m for mass percent. Sometimes it'll just have an m. I have seen weight before, if you ever see this, and sometimes just the one weight. We know that mass is the better way to say it, but sometimes it will be expressed that way. Volume, so sometimes a V, sometimes just one V instead of both V's. Mass volume percent is always going to have both, because if it was just M, it would be mass percent. If it was just V, it would be volume percent. So I do need both of them there. Sometimes, volume, sorry. I know that's old and it's not the best form, but sometimes you will see it that way. So just abbreviations. And then for mass volume, it's going to be the mass of my solute over the volume of my solution. The only one that's not going to be solution on the bottom, like I said earlier, is going to be molality. All the rest are going to be the total on the bottom. So mass of solute over volume of solution. And then if I want percent, or if I want parts per million, or if I want parts per billion, multiplied by the corresponding number. This one though, the units is where it's going to be a little bit different. So the units for mass must be in grams. If it's not in grams, you need to convert it to grams. For mass percent, right? Mass on top, mass on the bottom, it didn't matter what they were because they're going to cancel. They just have to be the same. For mass volume percent, my units have to be in grams. The units for volume must be in milliliters. So I'm going to have grams and I'm going to have milliliters. Again, for volume percent, it didn't matter as long as the units on the top are the same as the units on the bottom because they cancel. Here, they don't actually cancel, but we're not going to show them because it's assumed that it's grams per milliliter. So anytime you're calculating a mass volume percent, you can just do the percent sign or the ppm or the ppb. You don't have to show units. They don't cancel. Grams do not cancel milliliters, but it's standard to not show them because we know that it's grams per milliliter. They can't just be whatever. The standard is grams per milliliter. So you don't need to show units. Even though they don't actually cancel. It's very rare that we don't show units even though they have them. Usually you would lose points for actually not showing units unless they cancel. In this case, you don't have to. So don't need to show units even though they don't cancel. It's assumed to be grams per milliliter. So you need to have the mass has to be in grams, the volume has to be in milliliters. If that's the case, then you just don't have to show your units even though they have them. So this is actually, right, 9 different units of concentration. So mass percent, volume percent, mass volume percent, and then all 3 of those again for parts per million, and then all 3 of them again for parts per billion. I'm going to just go through the other units of concentration also, and then we'll kind of mix some examples up. So those were our percents, parts per million, and parts per billion. Molarity. I guess I had mole fraction next on that handout, but I just wrote down molarity, so we'll go with it. Molarity is one we already know. Our abbreviation is a capital M. And this is moles of solute per liter of solution. Let's actually do molality next. So we have those together. Molality is our new one. It's going to be a lowercase m instead of a capital M, so do be careful. It's going to be moles of solute. And then this is the one that's different on the bottom. It's going to be kilograms of solvent. Again, it's the only one that has solvent on the bottom. And then it's kilograms also, which is a little bit different. We don't have a lot of things where we're using kilograms. So molarity, moles of solute per liter of solution. Molality, moles of solute per kilogram of solvent. And then our last one, mole fraction. We did those in our gas chapter when we were dealing with partial pressures. That was moles of whatever the component is. Usually it's going to be the solute, but let's say you had sodium chloride dissolved in water and you wanted the mole fraction of water, then water would be the component, and that would be the number that would go on top, so moles of water on top. over total moles. Total being, again, moles of my solution. So our new ones up here, percent, parts per million, and parts per billion. And then we had 3 of each of those, and then molarity, molality, and then mole fraction. We're going to go through some examples next. So this one's kind of long because we're going to calculate a few different units of concentration. So I have a solution, and it's prepared by dissolving 17.84 grams of glucose, and our chemical formula for glucose is C6H12O6 in 250.0 grams of water. The density of our solution is 1.16 grams per milliliter, and we're going to calculate first our molality, then our mass percent, and then our last one, our molarity. So A first, remember molality is moles of solute, which is going to be glucose in this case. Remember, our solute is the one I have less of. So I have 17.84 grams of glucose and 250.0 grams of water. So glucose is my solute. And then that's going to be over kilograms of solvent. So water is my solvent in this case. So I do have grams of water, so we just need to move our decimal place over 3, right? Divide by 1,000 to get to kilograms. So that part should be pretty straightforward, and that's going to be the one on the bottom. And then moles of solute, I have grams of glucose. We have the molecular formula, so we're going to convert from grams to moles using the molar mass. So moles first. We're going to take our mass. We're going to divide it by our molar mass. So I'm grabbing my calculator. I have 6 carbons with an atomic mass of 12.01 AMUs each. Remember, we're going to change then our units from atomic mass units to grams per mole. So I'm just grabbing that off the periodic table. I have 12 hydrogen, so 12 multiplied by 1.01. Sorry, I'm hitting the wrong button here because I'm talking while I'm typing. And then I have 6 oxygen. And then we're just adding all of that together. And I end up with my molar mass of glucose, we'll just write it up here, of 180.18 grams per mole. So I'm going to divide by that number, right? I need grams to cancel. So since grams are on the top, grams are going to go on the bottom. So grabbing my calculator again. And I get 0.09901 moles of glucose. So as usual, I should have said this at the beginning, it would be great if you would do the calculations with me. So at any point, just hit pause, kind of work through it, because you are going to need to be able to work through them on your own eventually. And then when you're ready, just hit play again. So moles of glucose, let's do our kilograms here. I am just going to move the decimal place over, but do remember that there's 1,000 grams in 1 kilogram. So if you did want to set it up using dimensional analysis, because I have grams on top, I would divide by 1,000. which essentially means I'm just going to move this decimal point over 3 places. So I'm going to have 0.2500 kilograms. So to calculate my molality, I'm going to take my moles of my solute, 0.09901. I'm going to divide it by kilograms of solvent, 0.2500. And I'm grabbing my calculator again. And I got my molality to be 0.3960. And then for units, just like with molarity, right? With molarity was moles over liters. I could write moles over liters for my units, or I could put a capital M. My abbreviation for molality is a lowercase m, so I can write it that way. If I wanted, I can leave it as moles per kilogram, and that's also fine, right? Moles of solute per kilogram of solvent. The way that we would say this lowercase m is I would say molal, right? If I'm using the lowercase m as an abbreviation for the unit, it's molality. If I'm using it as a unit, that's said kind of strangely, I would say molal, right? If I had a 0.4 with a capital M, I would say it's a 0.4 molar solution, right? Could say the molarity is 0.4. So in this case, I have a 0.3960 molal solution, or I could say the molality is 0.3960. So if you're using that capital M as your unit, molal is how we would say it. If it was molarity, molar. Part B is going to be mass percent. So mass percent is going to be mass of my solute, which is going to be my glucose again. And then remember, it's over the mass of the solution. And then because I want percent, I'm going to multiply it by 100. Remember, if we wanted parts per million, I would do mass of solute over mass of solution and then multiply it by a million, right? 10 to the 6. If I wanted parts per billion, I would multiply it by 10 to the 9th. That's the only difference as far as the setup for these guys. It is solution on the bottom. I started talking about that. Remember, solution is the total. So the mass of my solution is going to be the mass of my solute, which if I go back up was 17.84 grams, plus the mass of my solvent, which is 250.0 grams. So I need to add those two together, and that's the number that's going to go on the bottom. So be really careful. Molality was per solvent. All of my others are going to be per solution. So I'm adding, and I got 267.8 grams of solution. So mass of solute, 17.84 grams. Mass of solution, 267.8 grams. My grams are going to cancel, and then we're going to multiply that by 100 because we're solving for percent. So grabbing my calculator. And I got 6.662%. One more. And again, please, if you want to just try these on your own, it would be a really good idea. Our last one is molarity. Molarity is moles of solute per liter of solution. So again, note it is solution on the bottom. I do have the mass of my solution up above. I need to convert from mass to volume. And if we go back up to the problem, we are given density as part of the problem. So I'm going to use the density to convert between mass and volume. My units are going to come out milliliters, then we can convert that to liters. So going back down, I have 267.8 grams of solution. And I'm just taking that from up here, right, where we already calculated it. I'm going to divide it by my density, right? I want to divide because I want grams to cancel. So I'm dividing it by my 1.16 grams per milliliter. So typing that into my calculator. And I ended up with 231 milliliters. I do need to convert that to liters. So remember there's 1,000 milliliters in 1 liter. So I would divide it by 1,000 to get milliliters to cancel. I'm just going to move that decimal place over. And I end up with 0.231 liters when I do that. So my molarity, moles of solute, which we calculated up here somewhere, 0.09901. Divided by my liters of solution, which we just calculated to be 0.231 liters. And then divide that out. And I got my molarity to be 0.429, and then either a capital M or moles per liter. Again, if you put the capital M, we're going to say molar. So this is a 0.429 molar solution. I want to do another example using parts per million. So let's say, what is the concentration in parts per million if 12.4 milligrams of sodium chloride is dissolved in 7.48 kilograms of water. So this one I'm not specifying if it's mass percent or volume percent or mass volume percent. We're actually just going to get that based on the units that are given to us. So I'm not given a density, so I don't have a way to convert between mass and volume. The problem doesn't specify, and I'm given mass for both my solute and my solvent. So I'm going to do mass parts per million. So mass of solute, which is sodium chloride in this case, over mass of solution, which again is going to be the total. And then because I want parts per million, we're going to multiply it by 1,000,000. So I'm going to have mass of sodium chloride, right? That's my solute, over my total mass, right? Mass of solution. And then I'm going to multiply it by 10 to the 6. Remember when we're doing the mass, whether it's percent, parts per million, or parts per billion, and then the volume ones, whether it's percent, parts per million, or parts per billion, the units don't matter as long as they're the same. So I need to get the units for my sodium chloride the same as my units for water, the same as my units for my total mass. Right now, one's in milligrams and one's in kilograms. It honestly doesn't matter what I convert it to. I can convert them both to milligrams. I can convert them both to kilograms. I can convert them both to pounds if I really wanted to. It really doesn't matter as long as I convert them both correctly and I convert them to the same units. What I'm going to do is I'm going to choose to convert them both to grams. Since milligrams is below my base unit and kilograms is above my base unit, if I went from kilograms to milligrams, I would actually go through grams. And if I went from milligrams to kilograms, I would also go through grams. So what I'm going to do is I'm just going to convert them both to grams. For me, that's the easiest way to do it. So if I have 12 right? 0.4 milligrams. And I know there's 1,000 milligrams in 1 gram, right? I would divide by 1,000. So what I'm going to do is I'm just going to move that decimal place over 3, and I'm going to have 0.0124 grams, right? If we move it back 1, 2, 3, I get that 12.4. And certainly if moving the decimal place again is confusing, don't do it that way. Actually just divide it by 1,000. So that's going to be my number of grams of sodium chloride. If I have 7.48 kilograms, and I know there's 1,000 grams in 1 kilogram, right? This time I'm going to multiply by 1,000, right? I would want kilograms on the bottom, so the 1,000 would go on the top. So this time I'm going to move my decimal place 3 places in the other direction, and I'm going to get 7,480 grams. Again, if we wanted to double check, 1, 2, 3, I'm back to my original number. And like I just said with the milligrams, if you want to type that into your calculator, by all means do it. So that's my number of grams of water. Remember, it's total on the bottom. So what I'm going to take is I'm going to take 0.0124 grams on the top, right? My mass of sodium chloride. And then on the bottom, I'm going to have the total. And you can add them ahead of time, or you can just do like I'm doing right now. I switch it up. Up above, when I was doing mass percent, I added them together before I put them into my little formula here. Now I'm doing it at the same time. However you want to do it, it has to be the total on the bottom. And then I'm going to multiply that by a million. So 0.0124 plus 7,480 for the bottom. Don't forget to multiply it by 10 to the 6. And I get 1.66 parts per million. Another type of problem that we could go through, and we did a few of these earlier when we talked about molarity in chapter 6, which we did with chapter 2, where we're given the unit of concentration and then we use that to determine something else. Remember, anytime we're given the unit of concentration as part of the problem, we're going to write out what it is. So an example for us, and say how many grams of sodium chloride do we need to prepare 1.50 liters of a 0.124% solution. And then this is going to be a mass volume percent. If I don't tell you, then again, use the units as part of the problem to determine it. So we're solving for grams, we're given liters, so mass volume. Sometimes I will have you convert from one to the other, but you would need a density or some other number as part of the problem. So this one, we're solving for mass of my solute. I'm given the volume that I need, and then I'm given my percent solution. And it is a mass volume. So again, be really careful. The first thing I'm going to do is I'm going to take this number and I'm going to write it out. Remember that percent means per 100. So what I'm going to do is I'm going to take the 0.124 and I'm going to get rid of the percent sign and I'm going to put it over 100 because that's what it means. I know that it's a mass volume percent, so I know that my mass is given in grams and my volume is going to be milliliters, right? Anytime we have mass volume percents or parts per million or parts per billion, my mass has to be in grams, my volume has to be in milliliters. We don't show those units, but it's assumed to be grams per milliliter, right? So this is a 0.124% solution, right? If I was to work this out, I get 0.124. So again, anytime, and this isn't just true for molarity, right? Anytime you're given a unit of concentration as part of your problem, write it out. Because what we're going to now use it for is we're going to use it as my conversion factor. right? I'm going to use it to convert between mass of sodium chloride and volume of solution. So once we have that worked out, I'm just going to go back up to my problem. Here, this is given to me in liters. This is in milliliters, right? Grams per milliliter. So I'm going to convert this to 1.50. We're going to move that decimal place over 3 places, and I'm going to have 1,500 milliliters. Again, if moving the decimal place doesn't work for you, we know that there's 1,000 milliliters. Oh, not milliliters, milliliters. 1,000 milliliters in 1 liter. So you would multiply by 1,000, right? We want liters to cancel. So I'm going to take this number, right? That's the number of milliliters of solution I have for my problem. Using my percent, right, as my conversion factor, since milliliters are on top, the 100 milliliters are going to go on the bottom, and 0.124 grams are going to go on the top. Those are going to cancel. So I'm typing into my calculator. And I get that I need 1.86 grams of sodium chloride. So again, anytime you're given a unit of concentration as part of the problem, please write it out, right? We're going to use that then to solve for something else. And it's a lot easier to try to figure out, do I multiply it or do I divide by it if I actually have those units, right? When I have these here, I know that to get milliliters to cancel, I have to multiply. If I was given a mass and I was solving for the volume, then I would have to divide by it, right? Because I would want my masses to cancel. So the percent sign isn't very useful, but once I write it out this way, it's generally a little more obvious as to what you need to do. So please always write those out. I want to go through one more example, and this one's going to be a little more complicated. What I want to do is convert from one unit of concentration to another unit of concentration. So what is the molality of a 0.243 molar sodium chloride solution? And we'll assume that this is an aqueous solution, so it's in water. And then the density of the solution is 1.002 grams per milliliter. And I just totally made up that number. It's probably close. It's a pretty dilute solution, so the density is pretty close to the density of water. So what is the molality of a 0.243 molar sodium chloride solution? The density of our solution is 1.002 grams per milliliter. Let's also calculate the mole fraction. We haven't done any mole fraction ones yet, so what is the mole fraction also? And then whenever we do mole fractions, we should say what it's a mole fraction of. So what is the mole fraction of sodium chloride in this solution? So that'll be my component. We could have asked for water if we wanted. So the first thing I'm going to do is, because I'm given a unit of concentration in the problem, I'm going to write that out. When I say I do that every time, I truly mean that. So what I have is 0.243 moles of sodium chloride for every liter of solution. Right? That's what we have. What we're trying to get to, right, is we're trying to get to moles of sodium chloride, which is no problem because we know that number, right? I can even write it in here. Let's actually move this over so we have a little bit of room. I have 0.243 moles of sodium chloride, right? The number of moles haven't changed just because I'm trying to calculate a different unit of concentration. But then I'm trying to get that in terms of kilograms of solvent, which is just water, right? So In my molarity, I have the total on the bottom. It's in terms of volume. What I'm trying to get to is just the water on the bottom in terms of mass. I can convert between volumes and mass using my density, right? That's what my density is going to do for me. And then once I do that, if I have the total mass, I can subtract the mass of sodium chloride from the total mass. That'll leave me the mass of water. So that's our plan. So if I have 1 liter, right, that's equal to 1,000 milliliters. So I'm going to take the 1,000 milliliters. I'm going to multiply it by my density, 1.002 grams per milliliter. Those milliliters are going to cancel, and I'm going to have 1,002 grams of solution. And then again, remember, my solution is my total, right? This is the mass of sodium chloride plus the mass of water, right? That's what this number is representing. It's supposed to be a bracket. So I want just the mass of water, right? So what I'm going to do is I'm going to calculate the mass of sodium chloride, which I can do, right? I have the number of moles. If I have moles, we can convert to mass using the molar mass. Once I get that number, subtract it from my total. So mass of sodium chloride, I have 0.243 moles. The molar mass of sodium chloride, I have 1 sodium, so 22.99, plus the mass of chloride, I get 58.44 grams per mole. I want to multiply by my molar mass so that moles cancel. And that gives me 14.2 grams of sodium chloride. So I have the mass of the solution, I have the mass of sodium chloride. So if I then subtract those two numbers, that's going to give me my mass of water. So 1,002 grams minus 14.2 grams. And I'm getting my calculator again. That gives me 988 grams of water. Molality is kilograms, so we're just going to move that decimal place over 3, and I'm going to have 0.988 kilograms of water. So I now have the number on the bottom, so we'll finish it out in a minute, but kind of again, the trick of it, write out what you have, right? Look at what we're trying to convert to. Moles to moles, not a problem. Here I'm going from volume to mass, so that's where we used our density to convert between the two. And then I'm going from the total, right? Solution is the total, to just my solvent. So that's why we had to do this subtraction, right? This is my total mass, right? My solution is my total. This is my solute mass. So when I subtract that, I get my solvent mass. And then we just had to convert it to kilograms. So we can finish up the problem now. I'm going to go do it up here in this little bit of space that we have. So I have 0.243 moles of sodium chloride. I'm going to divide that by 0.988, right? That's the number we just got down here, kilograms of water. And when I do that, I got 0.246 molal, right? Lowercase m as my abbreviation for molality. So what is the molality of a 0.243 molar solution? It is 0.246 molal. If your solution is dilute, which this is, right, is 0.2 something, it's not like 22 point something. If it's dilute, your molarity and your molality are going to be very close. So if I would have gotten like 36 as my answer, I know I goofed up somewhere. So 0.243 and 0.246 are pretty close to each other. So I'm feeling pretty confident that I did it correctly. Again, if it's dilute, if it's concentrated, they're not going to be that close. But if it's a dilute solution, those two numbers are going to be pretty close, right? If it's a dilute solution, it's mostly water, right? If I go and look at these numbers, my mass of solute here was much smaller than the mass of my solution. So most of it is water. So pretty dilute. I also have mole fraction. Okay, so let's calculate the mole fraction of sodium chloride. So to do that, we want moles of sodium chloride. And we want that over our total moles, which is going to be moles of sodium chloride plus moles of water. So moles of sodium chloride we already have, right? That's given to us in the problem. So again, the 0.243. And then on the bottom, 0.243. And then we have to add to that moles of water. I do have my mass of water. So I have 988 grams. I can divide that by the molar mass of water. So 2 hydrogens and 1 oxygen comes out to be 18.02 grams per mole. So I'm just converting between my mass and moles using the molar mass, which hopefully you guys are pretty good at by now. And I get 54.8 moles of water. So then that's the number that's going to go up here. My moles are going to cancel. Remember, mole fractions don't have units, just a number less than 1. And I got a pretty small mole fraction, which makes sense because it's a pretty dilute solution. So 0.0044, it's going to fit 1. Again, no units, right? So again, just please, if you're given the unit of concentration as part of the problem, write it out. I promise it's going to help. If you can actually look at those units, it makes a little bit more sense, right? If we go back up to this one again, I had moles, I had to get to moles, that wasn't a big deal. I know I have to go from liters of solution to kilograms of water. And if you just have like this decimal sitting in front of your face with a capital M after it, and you're trying to go to a lowercase m, it's a bigger problem to wrap your head around, right? With mole fraction, when I wrote it out, moles of sodium chloride over moles of sodium chloride plus moles of water. Moles of sodium chloride we had from earlier in the problem, we had mass of water. We know the molar mass because we always have a periodic table handy, so we could calculate moles of water. So again, just if you had just had an X, it sometimes, you know, at least for me, I just look at that and it's not helpful. But if you can actually look at the units, it's generally a little bit easier to try to figure out, you know, where you're trying to get to.